A patient goes into the MRI bore, the magnetic field aligns their protons, and the machine fires a massive pulse. Instantly, millions of identical protons flip and emit a burst of radio frequency energy simultaneously. In a CT or X-ray scan, an energy beam strikes a physical detector grid to register exact locations. But this MRI echo has no physical coordinates. It arrives at the receiver coil as a single chaotic chorus of radio waves stacked entirely on top of each other. To extract an image from that noise, we have to artificially map the three-dimensional space. We do this through spatial encoding, deliberately manipulating the magnetic environment so protons at different locations behave in predictable, measurable ways. We isolate the anatomy step by step, axis by axis. We start with the z-axis to select a single slice, then map x-axis by frequency and decode y-axis using phase. Constructing this invisible mathematical matrix is what makes MRI possible. Knowing exactly how it's built is the only way to read the resulting image accurately and recognize when the physics of the machine create visual errors. In uniform magnetic fields, protons spin identically. To isolate the z-axis, we apply a magnetic gradient, stronger at the head, weaker at the toes. Now, each horizontal slice spins at a unique frequency. A calibrated RF pulse then flips only protons matching that specific frequency. We control the thickness of this anatomical slice in two ways. First, by adjusting the bandwidth. Transmitting a wider range of RF frequencies activates a wider band of protons, producing a thicker slice. Second, we can adjust the gradient itself. Applying a steeper magnetic gradient means that same RF pulse will only find a match in a narrow band of anatomy, resulting in a thinner slice. Because these protons were spinning at different speeds, they begin to drift out of alignment almost immediately. Before we can measure them, the scanner briefly reverses the gradient to pull the protons back into a synchronized phase. The z-axis isolates a two-dimensional tissue plane, but millions of protons still broadcast simultaneously. We must cut it into columns. Looking at our newly isolated slice, we face a problem. Since these protons all share the same z-axis point, they precess at the exact same frequency. A horizontal readout gradient is applied across the x-axis. Protons on the stronger right spin faster than the left, giving each vertical column a distinct frequency. But these differing speeds make the radio waves drift out of phase and destructively cancel each other out. To preserve the signal, the scanner introduces a negative dephase gradient right before the readout phase. This scrambles the protons early, so that when the actual readout gradient activates, it forces the signals back into alignment. The moment these radio waves perfectly realign, they produce a maximum spike in amplitude. This forced realignment is called the gradient echo, time to peak mid-collection. To decode this tangled composite echo, we apply the Fourier transform, a mathematical function that extracts each underlying frequency and its amplitude. Knowing the x-axis gradient slope, the transform assigns each extracted frequency to its specific vertical column on the grid. Once the frequency determines the column, the height, or amplitude, of that specific wave dictates the physical brightness of that coordinate. We locked the z-axis slice, mapped the x-axis vertical columns, now we find the horizontal rows. In a single vertical column, every proton spins at the exact same rate. To find a y-axis position, we must distinguish the top from the bottom. We achieve this through phase shifting, a temporary y-axis phase encoding gradient pulses, forcing top protons to spin faster. When switched off, protons return to their shared speed, but their starting angles, or phases, are permanently staggered. A single static snapshot isn't enough to solve coordinates. To map these angles, we must watch how they evolve. The scanner repeats the sequence multiple times, changing the y-axis gradient strength each pass. Increasing gradient strength applies a larger kick to the proton's phase. Across repeated cycles, the phase of a proton at a specific y position begins to rotate in a predictable rhythm. Tracking phase rotation across cycles reveals a rhythmic pattern. The angle shifts by larger increments each pass, creating a measurable wave of phase change over time. The frequency of this phase change depends on location. Protons at the steep ends of the gradient undergo rapid phase evolution, while those near the center change very little. We can now apply a second Fourier transform, but this time it analyzes the frequency of phase evolution across the different cycles. This extraction provides the final coordinates for the y-axis. Layering slice selection, frequency readouts, and phase shift cycles sorts the radio waves. The chaotic echo is finally forced into a perfectly readable 3D matrix. We've built the grid. The z-gradient isolates the tissue slice. The x-gradient sets the frequency columns, the y-gradient shifts the phase rows, and the Fourier transform calculates the geometry. But this mapping relies on flawless sampling. When physical limits are pushed, the machine misplaces anatomy on the grid. This diagram shows the cause of aliasing, or wraparound artifact. The scanner converts the analog radio wave into digital data by sampling it at specific intervals. If the wave is not digitized frequently enough, the system loses the true shape of the signal. This failure is governed by the Nyquist limit, which states that accurate sampling requires a rate at least double the highest frequency in the signal. If the sampling rate falls below that threshold, the data points connect to form a false low-frequency wave. Because the Fourier transform relies on frequency to assign physical location, it interprets this false low-frequency signal as coming from the opposite side. Anatomy physically located outside the field of view wraps around and overlays the scan. Aliasing is a sampling failure, but the grid can also break because of the core assumption built into the frequency x-axis. The x-axis algorithm functions on a single premise. It assumes that any variation in precessional frequency is the result of the physical magnetic gradient, but human tissue has distinct molecular environments. Even in the same magnetic field, protons embedded in fat precess at a slightly lower frequency than protons embedded in water. The Fourier transform cannot distinguish a natural chemical frequency shift from a physical one. It simply reads the lower frequency of the fat, assumes it must be physically located further down the gradient, and shifts the fat pixels away from the water pixels along the frequency encoding axis. These misregistrations are inherent results of the spatial encoding process. A radiologist must master these mechanics to recognize exactly when and in which direction the hardware's own logic is creating a false image.